Hi, thanks for joining me. Today I'm going to be proving Pythagoras' theorem. Now before you click off the video thinking you've seen this proof before, what I'm going to be showing you is a non-standard proof. And all it's going to use is some elementary calculus. So let's just have a quick recap of Pythagoras' theorem. It says if you've got a right angle triangle like so, with side lengths A and B for the shorter sides, and then the hypotenuse C has length C, then A squared plus B squared equals C squared. Anyway, let's get into the non-standard proof. Okay, so what I've drawn on the whiteboard here is the right angle triangle, the ABC right angle triangle. So the base is A, clearly, because that's the origin of our xy plane. This is A, this height here is B, and I've called the hypotenuse C. And then I've sort of drawn on this quarter circle here. So obviously if I extended this, this would be a full circle, but I'm only focusing on the positive quadrant. So this is a quarter circle, and it clearly has radius C. Now what we want to do is derive the equation of this quarter circle. Now, you probably already know what the equation of a circle is. It's x squared, or x minus the x coordinate of the centre squared, plus y minus the centre of the y coordinate of the centre squared, equals radius squared. So in this case that would be x squared plus y squared equals c squared. But to derive that, generally we use Pythagoras' theorem. But of course here we're trying to prove Pythagoras' theorem, so we can't just write down the equation of a circle like that, because then we get a circular argument. So we've got to derive the equation of this circle in some other way, and the way we're going to do that is just by elementary calculus. Okay, so let's just take an arbitrary point on this circle, or this quarter circle. Let's say that point there. And then I'm going to draw the radius up to that point there. Now firstly, what's the gradient of this line here? Let's call it M1. And it's going to precisely equal, if I call this point here xy, is just going to equal y over x. Okay, pretty standard. Now, if I'm going to look at the tangent of the circle here, so if this a circle we want to derive the equation for, let's suppose it has y equals f of x. So we want to derive what f of x is. So we know that f prime of x, in other words the tangent at this point here, is going to be the gradient of this line here. But sort of by some basic circle theorems, we know that this thing here is perpendicular to this thing here. So we have that this line, the gradient of this line times the gradient of this line equals minus 1. Whenever you have two perpendicular lines, their gradients will always multiply to give you minus 1. So the gradient of this guy here has to be 1 over m1, or sorry, minus 1 over m1, and that of course equals minus x over y. So we get f prime of x, which I'm just going to write as dy dx, where y is the equation of the circle, equals this thing here. So dy dx equals minus x over y, which we're going to solve in just a second, but we also need to have some sort of initial condition. Can we get an initial condition from this? Yes we can, because if we look at when x is 0, what does y equal? That's that point there, but notice that that thing there is precisely a radius of the circle, so that we get that. So then we get that y at x equals 0 must be a radius of the circle, so c. Okay, so we've got a differential equation equipped with an initial value. Let's solve this differential equation using this this data, and then hopefully we can get the equation of the circle, and then from that we can derive Pythagoras' theorem. Okay, so we have dy dx equals minus x over y. So let's bring the y onto this side and dx onto that side. So we've separated the variables. So then we'll get that the integral of y dy is equal to the integral of minus x dx plus some constant, but I'm not going to call it c for obvious reasons, so let's just call it d. So the integral of y dy is just a half y squared. The integral of minus x dx is just minus a half x squared, and then plus d. So bringing the minus a half x squared onto this side and then multiplying through by 2 gives us that x squared plus y squared is equal to 2d, which I'm just going to call this thing here d tilde. Because remember, d is a constant, so certainly 2d is some constant, so I'm just going to call that d tilde. Now we're going to use our sort of initial condition, our data, that y evaluated at 0 is c. So when I plug in x equals 0 and y equals c, what do I get? 0 squared plus c squared equals d tilde. So 0 squared plus c squared is obviously just c squared, so I get that d tilde is precisely c squared. So then I can conclude that the equation of my circle is x squared plus y squared equals c squared. Okay, so that's the equation of my circle, which I've just derived sort of using calculus and geometry. And now I guess the thing to notice is that the point here, which is AB, certainly lies on my circle. So I can just plug in x equals a and plug in y equals b, and then that concludes Pythagoras' theorem. So a squared plus b squared equals c squared. And that is the end of the proof for Pythagoras' theorem. A cool non-standard proof to Pythagoras' theorem. Obviously there are some classic ways to prove it sort of by drawing the right angle triangle 4 times and then sort of comparing areas. But this is the way I'm showing you today, which I think is quite cool. Anyway, if you are new here, please do consider subscribing and checking out some of my other fun maths videos as well. That's all for today. I'll catch you in the next one. Have a great day.